we are going to show that this norm 2 is a norm on Rn. So first we recall about the definitions of norm 2 on Rn. So let x belongs to Rn, then the function's norm 2 is defined as square root of x1 square plus x2 square plus xn square. So now we are going to show that this is the norm, and for that we need to validate few properties on Rn. We have to validate these three properties for the definitions here. So first property we want to show it. First one. So clearly, since this is x1 square, x2 square, and xn square, so clearly this will be always positive or greater than equal 0. Okay, so clearly norm of x2 is greater than equal 0 as we have as x1 square plus x2 square x3 square plus xn square is always greater than 0 for all x1, x2, xn, and the equality 0 will happen. Okay, now x1 square plus x2 square plus xn square is equal 0 if and only if all xi is equal 0 for I is equal 1 to up to n. So therefore, if all xi is 0, that means norm of x2 is equal 0 if and only if x is equal 0. Now come to the second property. So for the second property, so norm of alpha x2. So therefore, since x is equal Rn, so with x1, x2, xn are the component, so we'll have here, this will be defined as alpha x1 whole square plus alpha x2 whole square plus alpha xn whole square. So this is, we separate it, so it will be each part we can take out the alpha. So we can rewrite it as alpha square x1 square x2 square plus xn square. So alpha square can take out with the square root, so which can be written as absolute value of alpha, and then the remaining part is x1 square plus x2 square plus so on xn square. So which is nothing but this square root is same as here, so it will equal norm of x2. So this will validate the second property. Now the third one is the triangular inequality. Okay, so to verify the third property, let we have already x belongs to Rn with the component x1, x2, xn, and let y is equal y1, y2, yn belongs to Rn. Then we have x plus y is equal x1 plus y1 x2 plus y2 and xn plus yn. So therefore norm of x plus y, this is equal, we will have here square root of x1 plus y1 whole square plus x2 plus y2 whole square plus xn plus yn whole square. So this is the definitions of norm of x, y. But we can write it here that, so this implies norm of x plus y to its whole square, x1 square plus 2x x1 y1 plus y1 square plus x2 square plus 2 x2 y2 plus y2 square. So plus this, so on. The last one is xn square plus 2 xn yn plus yn square. So this is equal. Now we'll just take the x component and y component part. So you will get it here, x1 square plus x2 square plus xn square, then plus yn square y2 square yn square, and the remaining part is 2 x1 y1 plus x2 y2 plus xn y. So the first part, this part we will have here. Okay, so now this is equal, this first part will gives us norm of x2 whole square plus the second one y2 whole square, and this third one is 2 inner product x y. Okay, so now since this one, and which we can rewrite as, so this is less than equal, and this will put absolute value of x y. Now we left to this inequality with work on this. So this is by the Cauchy inequality. So we can write it here, norm of x2 whole square plus norm of y2 whole square plus 2 into norm of x, norm of y. So this part is by CR inequality. This part is by CR, means Cauchy-Riemann inequality. We did it in the previous lecture. So therefore we can write this is as norm of x2 plus, basically this is x2. So norm of x2 plus norm of y2 whole square. So therefore by taking the square root we will get it here, x plus y2 is less than equal norm of x2 plus norm of y2. So this complete that norm of x2 is a norm on R2. So therefore is a norm on R2.